here, XX, yes. Thanks, Frederick, for the introduction. So today's talk is going to be concentrated on the new results we have. It's an ongoing work on the uptake of glyoxal on various mineral surrogates and natural dust samples. Well, Michel made a nice introduction, but since we are in the beginning of this conference, I think it's important to mention a few information about the context related with mineral dust. Here in this pie chart, you can see the average emissions of major aerosols every year, and as you can see, soil mineral dust represents around 43%. Therefore, is a big part of aerosol emissions. And the major source of mineral dust in the atmosphere are the arid regions of Saharan, Saudi Arabia, and Asian deserts. And here, as you can see, this is a video actually from GEOS model where it simulates the movements of aerosols in our atmosphere. Mineral dust can travel 1,000 kilometers away from the origin, and thus has a global distribution. Dust also plays an important role on climate, as you can see here, this is just a figure of the direct impact of radiative forcing of the different type of aerosols. Each color box represents a different type of aerosol. The solid line in the box is actually our best estimate on the radiative forcing, and the height of the color box is a measure of the uncertainty actually we have. So actually for mineral dust, we know that, well, our best estimate is that it cools the planet, but the uncertainty is quite high, and this is mainly due to our incomplete understanding of aging of the particles in the atmosphere. It means how their physical, chemical properties evolve after they are released in the atmosphere. Mineral dust also plays an important role on air quality. Organic or inorganic pollutants or even radicals can interact with mineral dust particles, and thus their budget is modified in the atmosphere, and as well as the properties of the dust also are changed. So in this framework, so in this context and in the framework of the CLIMDO project, we aim actually to investigate the heterogeneous interaction of dust particles with organics, and we focus particularly on glyoxal and methyl glyoxal. And the scientific objectives we would like to answer are how efficiently glyoxal, methyl glyoxal is taken up on the dust particles, how the atmospheric conditions can impact this uptake, and what's the impact of this organic aging on the optical and hygroscopic properties of the particles. So in today's talk, I'm going just to focus on the first objective. As I mentioned, this is ongoing work, and we will concentrate on glyoxal uptake. Now, why we selected glyoxal? So glyoxal is the final product of VOCs, oxidation by atmospheric radicals. And it is also an important source of HOX species in the atmosphere, and plays a key role in the formation of secondary organic aerosols. In general, is a key atmospheric species that participates in both homogeneous and heterogeneous photochemical reactions that affect both air quality and climate. Now, working with glyoxal is quite challenging, simply because it's not commercially available in its pure form. So in the lab, we have to make the synthesis, and this synthesis is achieved by mixing equal amounts of glyoxal trimer, which is actually dioxine, with phosphorus peroxide, and under heating and vacuum, we are able to isolate glyoxal monomers in a liquid nitrogen trap, and you can see them in yellow color here. We made the quality control in order to know the purity of our product, and we found using FTR spectroscopy and mass spectrometry that we produce glyoxal monomers with a yield greater than 99%. And this was used as a source of vapor during our experiments. Now, since we want to provide quantitative data, it's important actually to know some key physical and chemical properties of the particles we've used. So here you can see the list of the mineral surrogates that we have used and the natural mineral dusts. I don't have time to enter so much in details. We present a specific surface area of all the surrogates, and concerning the natural mineral dust, for some of them we have the complete composition. It means the surface and the bulk using XPS or ICP-MS analysis. But for some of them we don't. Samples are under analysis right now actually. What we could say is that the silicon content on the surface of the dust is lower than in the bulk, and for aluminium and iron this is the inverse. We have higher aluminium and iron content on the surface than in the bulk of the particles. XRD analysis also revealed that the major mineral oxide we have is quartz. There is also calcite in most of the samples, and the samples are also contain also clays. And you saw previously actually the experimental setup was very well described by Michel. So we've done these experiments in a Knudsen flow reactor, which actually is designed to study heterogeneous processes between gas phase species and aerosols, bulk aerosols. So here you can see a simple representation, and here is a real photo of the system. The reactor is applied with different lines that we use actually to introduce our gas phase molecule of interest, in our case glyoxal. There is again the sample compartment that we place inside the mineral surrogate, which is actually this sample compartment is isolated or exposed to the gas environment by moving a plunger up and down. And finally, there is an orifice at the bottom of the reactor where the molecules escape and goes inside a high vacuum chamber where we detect them using modulated molecular beam mass spectrometry. And here is how a typical experiment actually looks like. So initially we collect, we selected to present the uptake of glyoxal on quartz mineral. Initially, we collect the background of our instrument. Then we introduce glyoxal inside our reactor, keeping the surface isolated, and we have a steady state concentration inside our reactor. As soon as we expose the surface, we observe a fast decrease of glyoxal concentration that finally has a recovery with time. And after several minutes where we observe a stable consumption of glyoxal, we isolate the system, the surface once again in order to determine the initial concentration. Then we close glyoxal, we go back to the background levels, and actually we empty the reactor from the gas molecule, and then we move the plunger up and we see the desorption of glyoxal from the surface. So from this kind of experiment, we can obtain some useful information about the interaction of the gas with the surface. And the first one is the initial uptake coefficient that gives us actually an information about the affinity of the gas molecule with the fresh surface. The second one is the steady state uptake coefficient, which is measured after a long time and when we have a stable consumption of our gas. And this information actually is important for the aged particles. Both initial and steady state uptake coefficients are used in models, are used directly in models to make simulations, so the kinetic parameters used. And finally, from the integration of the adsorption peak, we can get the number of molecules of glyoxal removed from the gas phase and stored on the surface. So now let's move on the results section, and here you can see the initial uptake coefficients we obtained for the 20 different samples. First of all, the values we have obtained are quite high, are in the order of 0.1 for most of the samples, and they are very close to radical species. If we compare the values we obtained for iron minerals, we can say that they are pretty close, but when we compare the values obtained on calcium minerals, we see a vast variation actually, with the highest value measured for calcium hydroxide. And considering that we have also high values for titanium dioxide or magnesium oxide, it's the hypothesis that we currently doing is that glyoxal initially prefers to be adsorbed on hydroxylated surfaces, surfaces that contain OH, surface OH groups. But this is something that we need to validate. Now, concerning the natural samples, we have seen that dust originating from Asia have the highest initial uptake efficiency on glyoxal. And here is another data set actually of uptake coefficients, but this time this is a steady state uptake coefficient. This is the coefficient measured after a long exposure of the dust to glyoxal. And the values we obtain are in the order of 10 to minus 6. And this time we see contrasted behavior between the iron minerals. We see that hematite, for instance, has a significantly higher steady state value than magnetite or goethite. And this could be related with the oxidative state of iron in our sample. The highest values were measured for hematite, magnesium oxide, and calcium hydroxide. And from the chemical analysis that we are currently having, we can say that mineral dust containing magnesium and calcium appears to have the highest reactivity. That's why Gobi dust actually has the highest value among the different natural samples. And finally, here we present the total uptake capacity of the mineral dust, which means the number of molecules of glyoxal stored on the surface or taken up on the surface. Just to make, for the sake of comparison here, this line represents the theoretical monolayer coverage, which is actually the coverage of the surface considering a perfect packing. So for some mineral oxides like magnetite and titanium dioxide, we can see that the values we measure are above monolayer coverage. It means that we form multi-layers probably. Regarding the natural dusts, as we can see here, their values are below the monolayer coverage. But if we consider that quartz, which is the major mineral in our samples, has a very small uptake capacity, it's highly probable that we form islands of multi-layers on the particles. Locally, we form multi-layers of glyoxal on the particles. So I'm arriving at the conclusions. So what we observe in our study is that glyoxal is strongly taken up on the dust particles. Initial uptake coefficients are very close to those of OH and O3 radicals, for instance. Natural dust that contains that are rich in magnesium, calcium, iron, and potassium minerals appears to have high reactivity and uptake capacity. We anticipate the formation of islands of multi-layers of glyoxal on the particles. Glyoxal uptake or natural dust could be an important source, an important sink of the molecule in the atmosphere during dust events. And regarding the perspectives, actually, we need to increase the database of the natural dust. We still have 6 natural samples in the lab that we need to analyze and perform these kinetic measurements. If there are colleagues among us that could supply us with some samples, we could accept them with great pleasure, because this is something that we are missing actually, to create a database and evaluate the uptake of these organic molecules on various samples. And finally, we need to move forward and investigate the impact of environmental conditions on the uptake of glyoxal. Uh, yeah, that's it. I would like to thank you for your attention and for any questions.
Any question in the audience? Okay, you've got questions online, right?
Why do you think dust-rich magnesium, calcium, iron, and potassium minerals are more reactive?
Yeah, I mean, what I mentioned, like reactivity, are the steady-state uptake coefficients. So what I mentioned is that they have the highest values of uptake coefficients. And why I'm mentioning that is because we have the XPS analysis, and we compared actually the different samples, and we have observed that these samples that they have richer on these elements, they appear to have the highest uptake capacity and steady-state values.
Yes, Michel. On-site question.
Yes. Are you,
Michelle, please move people on side. I would like to submit a question. Should move to the microphone.
Okay. All right.
Otherwise, we have different microphones.
Yeah. Manolis, my question has to do with the fact with the interpretation of the steady-state uptake coefficient. Are you ready to speculate whether or not it's real reaction or just transport across the interface into the bubble?
Thank you, Michel. So difficult to answer. I can say that we don't have any gas phase products formed. So we don't have any gas phase products but it doesn't mean that we could not have some transformation on glyoxal on the surface. We think we form this kind of multi-layers, but we don't know actually if there is any other, let's say, chemical bonding between the glyoxal and the surface. It's chemisorption. This is something that will be interesting to evaluate. Maybe we could do that with our surface analysis, like using FTR spectroscopy on the surface.
Any other question in the audience or online, maybe, Xavier? No? No other question online? Okay.
I will share this with net. People said that we have a load of soil sample from Saran and China. Happy to share it or internet.
Okay, so we are going to expand.
Yeah.
Thank you. Thank you for the connection. Okay, so we move to the next speaker, and we can thank again Manolis, but he's going to come back later on. The next talk is online. It has been recorded before the conference by Maya Abou-Ghanem. So Maya is a PhD student in the group of Sarah Styler at University of Alberta in Canada. And she's going to tell us about the influence of organic coatings on the photochemical uptake of ozone by titanium dioxide. So we have already heard about titanium dioxide.
Hello everybody, and thank you for coming to my talk at this year's International Dust Conference. Unfortunately, I'm not able to be there with you in person, but I'm very happy for the opportunity to be able to deliver my presentation to you all virtually from Canada. So today I'm going to be discussing some of my PhD research that focuses on the photochemical uptake of ozone by organic coated titanium dioxide particles and the implication of these organic coatings on mineral dust photochemistry. So, as I'm sure most of us already know, there's over 1 billion tons of mineral dust emitted into the atmosphere each year, with one of the greatest sources for this dust being the Sahara Desert in northern Africa. And so what I'm showing here is just a NASA simulation of a Saharan dust event that took place in June of 2020, where we see dust being transported off the west coast of Africa, and within 10 days this dust makes its way past the Atlantic, where it's deposited in North and Central and South America. And to give you an idea of what this kind of looks like for people living in these regions that experience high dust loadings. I'm showing this picture here that was taken in San Juan in Puerto Rico on June 22nd of that year, where we see a person looking out at the horizon that's completely obstructed by dust aerosol. And if we fast forward a day later, this was taken in Quintana Roo in Mexico on June 23rd. And again, here we see a city in this region that is blanketed by a layer of Saharan dust. And so why do we care about this dust? Well, it has a lot of different atmospheric implications, but what my research focuses on in particular is the ability of this dust to serve as a reactive surface in the atmosphere for the uptake and degradation of pollutant gases. And so what I'm showing here is a Saharan dust event in Dakar in Senegal. And if we were to zoom in onto an individual mineral dust particle in the atmosphere in this photo, we may expect to see all these reactions taking place. So for example, laboratory studies have shown both the uptake of organic and inorganic pollutants is possible at the surface of dust, and in many cases this leads to the formation of new species formed at the surface, as well as new species formed in the gas phase. And interestingly, a lot of this chemistry is enhanced in the presence of light, which means that dust itself is also photoactive. And so what my early PhD work focused on was trying to understand this photoreactivity. And how I did that is I looked at individual naturally sourced minerals and I investigated their reactivity with ozone, which I used as a model pollutant. And so I'm just showing a subset of these minerals. These are just 4 of them. And underneath each mineral is their reaction profile with ozone. So these were studied in a coated wall flow tube. So these minerals were ground up into a powder. And shown in these figures here is ozone on the y-axis and time on the x. And the blue and yellow regions represent the reactivity of the mineral with ozone in the dark and in the light, respectively. So what we can see right off the bat is that each mineral has a unique reaction profile with ozone, but interestingly, we find that the same mineral phase, so for example, I had sourced 2 titanites from 2 different locations, is also unique. So, for example, with one titanite, I saw a significant loss of ozone in the light versus the other titanite sample. I did not see very much loss of ozone in the light. So this sample was significantly less photoactive than the other sample. And this was a good first step in trying to untangle the complexities behind mineral dust photochemistry. But as I previously mentioned, these experiments were conducted in a coated wall flow tube. And as a result, these minerals were ground to a powder and their surfaces for uptake were quite fresh. And we know that that's not the case in the real atmosphere. So for example, I'm just showing here a dust episode in Beijing, China. And if we were to zoom in onto an individual mineral dust particle, but this time look at its chemical composition, we may expect to see something like this. So this is a single particle mass spectra of an individual mineral dust particle sampled. I believe this was somewhere in the United States, but regardless, what we can see is that this mass spectra contains ions that are not related to the minerals that are present in mineral dust. So for example, we see lots of carbon and chloride, nitrates and sulfates. And what this means essentially is that mineral dust is often found internally mixed with other various pollutants. And again, a lot of the time this could be as a result of its reaction with pollutant gases during its residence time in the atmosphere. And this has also been shown in other studies as well. So I'm just showing a scanning electron microscopy image of an individual dust particle where we notice a particle morphology that has an outer shell and an inner shell. And when the authors investigated the chemical composition of the outer and inner shells, what they found was this was a dust particle that was coated with organics. And so that's what my research tries to address. It tries to address how do these organic coatings influence the inherent photochemistry of mineral dust? Does it suppress or enhance pollutant uptake? And also, how does the dust photochemistry change if we increase the thickness of these coatings at the dust surface? And how I aim to do that is using an aerosol flow tube reactor. This is something I had designed early on in my PhD. And so the particles that I'm using in this aerosol flow tube reactor is titanium dioxide. This is just a simple model for mineral dust. And the organic coatings that I'm using is icosane and decyl cyclohexane. Both of these have been detected in diesel exhaust, so they have some atmospheric relevance to them. And I'm just showing here a schematic of the aerosol flow tube setup, which I will quickly walk you guys through. So at the bottom here is a nebulizer which generates titanium dioxide aerosol that's then passed through a diffusion dryer to remove any water. And then titanium dioxide particles move into a coating apparatus that either contains icosane or decyl cyclohexane. This coating apparatus is heated to allow these organics to vaporize, and then it's cooled to allow for the condensation of these organics onto the surface of the particles. And depending on the temperature of this, as we increase the temperature, we are also increasing the coating thickness on the particles. And then these coated particles are then injected into the side of the aerosol flow tube. And then here at the top, we have a movable injector that introduces ozone. So depending on if it's pushed all the way down or pulled all the way out, we can control for the exposure of ozone towards titanium dioxide particles. And again, since we are studying the photochemical uptake of ozone, this aerosol flow tube is surrounded by 8 UVA lamps to capture a small region of the solar spectrum. And then at the bottom here, we have a scanning electrical mobility spectrometer to obtain the particle size distribution, as well as the surface area of the titanium dioxide particles, as well as an ozone analyzer to measure the ozone concentration over time. And if you're not a huge fan of schematics, I've also attached here just an actual photo of the flow tube setup. And what we can do with this setup is calculate an uptake coefficient, which is denoted by gamma here. And this represents the total amount of ozone taken up onto the surface divided by the total number of collisions that ozone has with the surface. And how we can calculate that is by obtaining a pseudo first order rate constant. This is determined by by using ozone concentrations in the presence and in the absence of titanium dioxide, as well as the mean molecular speed of ozone and the total number of dust particles and their surface area as well. So one important thing for these experiments was to optimize our dust generation technique with the nebulizer, and it's really important that the dust concentration stays the same throughout the experiment for us to be able to calculate these gammas appropriately. So at the beginning of the experiment, I noticed some strange things happening. So here I'm showing the total area on the left-hand side with the total number on the right, and then again, this is a function of time. And what we can see in this plot, where the blue regions represent time points in the dark and the yellow is time points in the light, is that anytime I turned on the light in the experiments, both the total area and the total number of particles would increase. And this was strange. At first, I wasn't sure exactly what was going on, but the more I looked into it, it seemed like it was an effect of photophoresis. And so during illumination, essentially, you are heating up parts of the flow tube, even though there is a water jacket that is there to control for temperature. This still did not prevent heating up sides of the flow tube that would result in dislodging titanium dioxide particles that were absorbed onto the wall and making these particles migrate towards the center and then get sampled out. So in order to try to reduce these photophoresis effects, to try to stabilize the total area and total number of particles over the time of the experiments, I played around with the temperature of the system, and by reducing the temperature, I was able to stabilize the number of particles getting generated, and I'm showing that here. So here I'm showing particle diameter as a function of time, and then the color legend here represents the number of particles per centimeter cubed. And what we can see is overall these are now constant when the temperature is reduced in the flow tube. And again, we also see a bimodal particle size distribution at around 700 and 1500 nanometers. So these are the size of the particles that are getting generated by the nebulizer. And so what we can do with this information now is look at the ozone uptake by organic coated titanium dioxide. So first off, I'm just showing an uncoated titanium dioxide particles here, where I'm showing ozone on the y-axis and time on the bottom. Again, blue and yellow represent regions in the dark and the light, and then these are with increasing temperature. And what we can see is that as temperature increases, the loss of ozone generally stays the same. But with the decylcyclohexane, we see that as temperature increases, the ozone loss decreases up until 75 degrees, where we see pretty much no loss of ozone at the surface. So this ultimately means that organic coatings are able to suppress the photochemical uptake of ozone by titanium dioxide. And what we can do with all this data is then go back and calculate those uptake coefficients, as I previously mentioned. And when we do this, we get data that looks like so. So I'm showing the uptake coefficient here as a function of, versus temperature. And I'm showing uncoated icosane and decylcyclohexane coated titanium dioxide particles. And what we can see is that as we increase the temperature, the uptake of ozone decreases. And in particular, it decreases the most with the decylcyclohexane coating compared to the icosane. And one reason for this could be because decylcyclohexane has a vapor pressure that's twice as high as icosane. So we may just be able to generate more of the decylcyclohexane in the gas phase when we're heating it, which ultimately leads to greater condensation onto the surface of the particles and thicker coatings. So the next steps for this project is to investigate the influence of shorter coatings, including N-heptadecane, to see when does this photochemistry become suppressed, at what time can, or at what viscosity is ozone limited to reaching the photoactive titanium dioxide surface. As well, we also want to try to obtain coating thicknesses using our scanning electrical mobility spectrometer by looking at changes in size distribution during the coating process to try to approximate coating thickness. And so, in summary, we were able to kind of answer some of these questions in this talk. Again, this work is still a little preliminary, but what we do know is that organic coatings can in fact suppress mineral dust photochemistry, and that the suppression is greater with thicker coatings. So this means that with organic coatings, ozone is unable to diffuse through the coatings to reach the photoactive surface. And this may have some implications for mineral dust photochemistry, again, as these coatings are observed on ambient dust aerosol. And with that, I would like to thank you for your time and your attention, and I'm happy to take any questions.